to the first lecture of the Kaiser Spring Lecture Series 2026, 1 in a million, looking for a second Earth. Today's lecture will be given by Dr. Melissa McClure, an assistant professor and VD laureate, a prestigious national grant awarded to highly promising researchers at Leiden University. Before coming to Leiden 7 years ago, she also worked at the Anton Planck Institute at the University of Amsterdam as a Marie Curie postdoctoral fellow, and at the ESO headquarters in Garching, Germany as an ESO postdoctoral fellow. Her main topic of research is in exoplanets, very fitting for this lecture series, and more specifically how solids like ice are necessary for life are incorporated from dense molecular clouds into beginning planets. In particular, she's the principal investigator of the James Webb Space Telescope Ice Age program. This program is intended to track precisely how the previously mentioned essential molecular ingredients of life are incorporated from dense molecular clouds into the planet-forming regions of the disks around young stars. For this lecture, the focus will be on the formation of exoplanets. How do exoplanets form? How can planet formation result in different planetary systems? What other rocky planets could be similar to Earth? And does Earth for planet formation produce carbon copies of Earth? I hope you enjoyed the lecture. Can you guys hear me? With the microphone. Good. Okay, excellent. Thank you very much for that great introduction. So I'm really excited to be here today, and it's not too bad weather out, so hopefully everyone was happy to be inside. To tell you guys a little bit about how we can start answering some questions about whether we can find other planets like Earth in our universe. So there are two big picture questions that we have right now in the fields of exoplanets, planet formation, and protoplanetary disks. And those are, how did we get here, and are we alone in the universe? And these questions can be sort of rewritten in the context of what we're about to talk about today as, how did life arise on Earth, and how do other planets, or do other planets like Earth exist in our universe? So when we think about Earth, one of the things that stands out to us is that Earth teems with life. And we have different types of life, like animals, plants, fungi, protozoa, bacteria. All of these things have in common DNA. And DNA is made up of molecules that are large molecules made up of multiple atoms of different elements. And the main elements that we see in DNA are carbon, hydrogen, oxygen, nitrogen. And if we look at our own bodies, we can see that these make up the vast majority of the elements that we see in our body, with about 0.6% left over for other elements that are not these. So I'm going to refer to these elements during the rest of the talk as CHONs, for carbon, hydrogen, oxygen, nitrogen, just as a short term, so you guys know what I'm referring to. Now, we think, from our own perspective, that because we see life all around us on Earth, that this must mean that Earth is rich in CHONs. But actually, when we look at Earth and sort of do a bulk estimate of how much of each element is in Earth, we see that Earth is actually heavily depleted of these elements. Most of Earth is actually rocky material like iron, magnesium, silicon, and there is lots of oxygen. It's sort of doing double duty as either a CHON or something, an ingredient that we see in rocks. So only a little bit of Earth, less than 1%, is actually hydrogen, carbon, or nitrogen, these elements which are really essential to life as we know it on Earth. So if we are looking at the composition of Earth, we think that the reason Earth is like this, relatively poor in these elements, is because of where it formed in our solar system and how it formed in the solar system. So Earth is one of 4 rocky planets that we see around our sun. And all of these rocky planets are small, they're gas poor, they're dry, they have very little water on them. And they have relatively little of these elements, the carbon, hydrogen, oxygen, and nitrogen. We also see 2 other types of planets in our solar system. Gas giants like Jupiter and Saturn, and these planets are much, much bigger, the largest planets in our solar system. And they do have more CHONs than are seen on rocky planets, mostly in the form of water ice and carbon dioxide ice. And then we have a third type of planet in our solar system, the ice giants, like Uranus and Neptune. And these are less big than the gas giants, but still much bigger than the rocky planets. And they're gas rich, and they have lots of ice, so lots of carbon, hydrogen, oxygen, and nitrogen. So we think that what we see in the solar system is caused by a compositional gradient that relates to the temperature structure in the solar system when it formed around our sun. And that's to say things near the sun are hotter, and things farther away from the sun are colder. And this means that you essentially create a region in the disk out of which our planets formed where you have snow line, and this is where you have ices further out in the colder regions of the disk, and inside the snow line you can't have any ice, you just have rocky material. It's sort of like what you see in this picture of a mountain here on Earth where above a certain altitude you have snow suddenly appear because it got cold enough for that snow to freeze out. And down closer to the lower levels of the mountain, that water is actually in the vapor state in the air around us rather than in snow. So the same thing is thought to have happened in the material from which the planets formed in our solar system. Now, we think that the reason that we have any chance on Earth at all is because they were delivered after Earth was formed by impacts of comets, like this comet 67P. You may remember a few years ago, ESA landed a probe on this. It was like the rubber duck comet. And on this comet, they had water, carbon monoxide, methane, carbon dioxide, ammonia. Also, they had a number of different complex molecules, sort of including some things like glycine, which are some of the building blocks that we have for biomolecules, like what we saw a few slides ago in DNA. So basically, we think Earth was poor in these elements. They were delivered externally from the cold regions of the disk. Now, just because Earth formed this way and had this composition doesn't mean that we should necessarily expect other planets that are rocky to have the same composition. We know now that there is a wide range of planets that have been detected, more than 3,000, and this artist's impression indicates with the colors, from cool colors to hot colors, sort of the range of temperatures that we expect these planets to have based on their locations away from their stars. And you can see that they also have a wide range of sizes for the planets as well. So we shouldn't necessarily expect that, that these planets all ended up, like all of the rocky planets, that they necessarily end up being like Earth. And in fact, when we look at some data from these planets, if we look at the number of planets per star on average versus the size of the planet, we can see in this distribution, if you sort of follow this black line, this is where Earth would fall in the distribution. This is where Neptune and Jupiter would fall. And we can see that the vast majority of planets that are detected actually don't align with either of these three examples of planets from our solar system. There's a bump right here for planets that are rocky planets, but they're larger than Earth. We call those super Earths. There's a second bump for planets that are still larger than Earth, but smaller than Neptune, and those are called mini-Neptunes or small Neptunes. So these two planets are, by number, the most frequently detected in our own galaxy. And they may actually have very different formation pathways and properties relative to Earth. So this means that if we want to have answers to these questions, like how did life arise on Earth, and do other planets like Earth exist, we actually need to sort of rephrase these questions as, should rocky planet formation commonly produce rocky planets that have compositions similar to Earth, i.e. carbon copies of Earth? So this is what the rest of the topic of this lecture will be about, whether we see evidence for planets that are very similar to Earth in terms of their carbon content and size or not, and how that relates to their formation pathway. So this is just an outline for the rest of the talk. So you see we've covered the motivation for why planetary composition is important to this question of Earth 2.0, or carbon copies of Earth. Then I'd like to go through a little bit about the formation theory for how planets form, whether we can tell something about this from the solar system meteoritic record, specifically for Earth and the other planets in our solar system. Then I'd like to make a comparison with observations that we have for protoplanetary disks to see whether or not what we learn about rocky planet formation from the solar system bears up in other systems. and then give you some conclusions. All right, so that was a little bit abrupt there. Let's start out with a basic introduction to how planets form. So planets are actually a byproduct of star formation, which is kind of funny to think of them as a byproduct because for us they're like the most important thing about this whole process, right? We care about them because we're on the planet. But planets essentially result from a process where a region of a molecular cloud, which are these finger-like projections you see here in this famous image from the Hubble Space Telescope, a region of this becomes very cold and very dense and starts to collapse. And as it collapses, it forms a star at the very center of it. And it's connected, the star is connected to the remainder of this core of material in the cloud by an envelope that funnels this material onto a protoplanetary disk. And that material spirals onto the central star. Over time, this envelope of material that connects the disk to the molecular cloud either drains onto the disk or is blown away over time naturally. And you're just left with a protoplanetary disk, and planets potentially form within this disk within about 1 million years after the initial collapse of the star. And then within 10 million years, this disk either turns into planets or is blown away. And then at that point, you have a planetary system, sort of like our solar system, where you have a star with multiple planets around it, and ideally, some of these planets would end up being rocky, like Earth. Now, if we focus for a moment on the protoplanetary disk stage, we can walk through the steps of the process of forming planets and show you how this process can be different depending on what outcome you get. So when we talk about planet formation, we need to go from solid pieces of rock that are the size of about 1 micron, which is less than the width of your hair, and they need to build up by a factor of 10 to the 12 in size. So that's like 12 orders of magnitude, all the way up to bodies that are like 1,000 kilometers in size, up to maybe 10,000 kilometers in size. And this is a huge range. At each stage of the process, these solids have a different piece of jargon that they're called for their names. So the smallest stage is called dust, when it's about micron in size. Once you reach about 1 millimeter, so something like the size of a little bit smaller than your fingernail or centimeter size, we call those pebbles. Then once you reach kilometer size, we call those planetesimals, and these are sort of the first large bodies that we'll see go on to form planets. And the planets are when you reach something that's around 1,000 kilometers in size. So I'll use these different terms throughout the rest of the talk. So when we have a basic recipe in any given disk for how we need to cook up planets. So if you look at this disk will have regions in it where it has both gas and this dust. Remember, the dust is the micron size pieces of solids. So you need to grow your dust first into solids that are more like these millimeter to centimeter sized pebbles. Once you've done that, then there needs to be a way to radially concentrate these pebbles in a ring. The next step is that within the ring, you have to azimuthally concentrate your pebbles like this, and then you end up cooking up a planet. We'll come back to this term later. This is very untechnical, but just it says as a placeholder. Once you have a planet, depending on the size of the planet, it may actually grow enough that it can open up a gap in this disk. And in this case, you can very clearly see the gap in observations. And there's still like a little bit of an inner disk left inside, and over time, material from the outer disk will push its way in, and you'll end up clearing out this inner gap and forming something like a rocky planet in there. So this is a basic outline of what we think happened in our own solar system. This only happens, though, if the outer planet here gets large enough. So we know first that when we talked about collecting the material in a ring, the pebbles in a ring, this is actually something that most astronomers will agree upon. We have a mechanism to do this physically. It's called radial drift. So this is because the dust that is orbiting in this disk orbits at some kind of fixed velocity at each radius. It's a Keplerian orbit. But the gas in the disk sees radiation pressure from the central star and it wants to get pushed out a little bit, which means that it goes a little bit slower than the dust. So the dust runs into it, and much like a Dutch bicyclist on a windy day, it sees a headwind, or really a Dutch bicyclist on any day, because I always get a headwind wherever I'm going. And it slows down the dust because it sees this headwind. And as it slows down, the dust will decouple from the gas and it will start to spiral in toward the central star at faster velocities than the gas moves. And you can think of this sort of like one of these demonstrations that you see sometimes at science museums, where you have this potential well that goes, there's like a hole in the center, and you take some marbles and have them spin around like that. You can think of the black part as the gas, and the dust particles as the marbles that want to spiral in toward the center. So this process causes all of these pebble-sized pieces of dust to collect, to move in toward the disk and collect closer in where they can start to form planets. However, the process of cooking up a planet is something that's still very controversial. We have many different ways to do this, and each way has its own astronomer who wants to argue passionately for this is the right way to do it. So the first way, which is sort of the traditional way that we've thought of for a long time, is so-called core accretion. So this is when you have basically step by step, two dust grains collide and make a larger dust grain. Eventually these dust grains turn into pebbles, two pebbles collide, and if you build up enough of that, they make planetesimals eventually, and those planetesimals collide to make planets. And this sounds really good in theory, except there's actually a problem called the meter barrier problem. And this basically means that once you have bodies that are about a meter in size, if you run two of them together and collide them, they actually fragment into smaller pieces, and they just don't build up to larger sizes beyond that point. So unfortunately, if you only had this type of planet formation, you would never be able to form things that were planetary mass because they would stop right here at 1 meter boulders. Because of this, there was an alternative that was proposed called a gravitational instability. This was a way to get around this meter barrier problem, where basically you take a large cloud of gas and dust in the outer part of the disk, where it's very cold and very dense, and you can just directly collapse that to form a planet. And this sounds good in theory for things like Jupiter, but it means you always form big planets. You can't form something like a rocky planet like Earth, so you skip right over that step. So this doesn't work for us. And then people sat down and thought about this for a long time. They said, aha, wait a sec. We don't actually need, we don't need a gravitational instability in the whole outer disk. We can actually do something called a streaming instability, which is just a very local instability in the inner disk. And you take, again, a smaller cloud of gas and dust and collapse that directly to form a planetesimal instead of something like a Jupiter-sized planet. And under the right conditions, this means you can form planetesimals, which are this first stage in the formation process of a planet. And then once you have those planetesimals, they can either collide via core accretion again. We can come back to this theory because everybody really likes this theory. And you could then eventually build up something like an Earth-sized planet from this. Or you could also take into account that there's a large supply of these centimeter-sized pebbles in this disk, and the forming planetesimal can actually eat up all of the pebbles around it and go that way very rapidly to form something like a Jupiter-mass planet. So currently these two are the preferred, or this whole sequence of events, the streaming instability to pebble accretion or core accretion, this is the preferred way that people think you form both rocky planets and giant planets. Now, if we look at what we see from observations, observations do show us in several protoplanetary disks, including PDS-70 and WISPIT-2. There are clear cases where we see a protoplanetary disk here, and then inside this gap, we actually see giant planets that have formed and are actually still building up their mass by eating up the disk around them. In this case, there are two. One of them is somewhere around a Jupiter mass. The other one is larger than Jupiter mass, and in this case also larger than Jupiter in its mass. And the problem is, these are probably gravitational instability examples because the planets that they build this way are so massive, and they're also located further out in their disks. So while these images are really, really cool, they don't actually tell us anything about rocky planet formation, unfortunately. So to do that, we have to look somewhere else. So that was planet formation theory. Now, where we look for rocky planet formation information is in the solar system's meteoritic record. And this is because it's so detailed, we have all of this information right here, we can actually get our hands on it as opposed to looking at it remotely. So in this sequence of events where we build up from dust particles through pebbles to planetesimals and eventually to planets, if we start with the planetesimal stage and then see how that develops from toward planets, and we look at the internal structure of this planetesimal and planet, we can see that at the first stage, the planetesimal stage, you basically have a pile of smaller particles that are all sort of jumbled together, like sort of like a dust bunny. It's not very well structured, everything's just stuck together. But over time, there's internal heating that happens, and this causes this planetesimal to essentially rearrange itself on the inside. And a lot of the heavy metals, like iron and nickel, sink to the inner part of the planet, the core of the planet, and they form a hot core. And meanwhile, the lighter materials that are like rocky materials, but not iron, rise up to the surface and form a crust. And this is how you get something that looks very much like the Earth, where it has an iron-rich core and a rocky mantle and crust around it. So this is what we think happens internally during this stage. And what we see on Earth is actually fragments of these different stages of interior evolution in the form of meteorites. So basically, there are types of meteorites, in this case, non-carbonaceous chondrites. I'm going to use some technical terms, but they're not too important. Two different types of meteorites trace the sort of unprocessed rubble piles into the planetesimals. And then there are two other types of meteorites, the iron meteorites and achondrites, that trace both the core and the mantle of the planets that got hot enough and big enough to restructure themselves on the inside. So these four types of meteorites can be used to tell us a timeline for how the solar system formed and how the rocky planets formed in the solar system. So if we start off and go through one by one and look at the different meteorites, if we do this, we can use them. Each of the meteorites has different heavy atoms in them. So for example, hafnium, tungsten, and thorium, and they have different isotopes or different numbers of neutrons in some of the elements. And we can use these to age date when the planetesimal from which they first came together, and come up with a timeline for that. We can also use the composition that they have in terms of how carbon-rich they are relative to, say, another element like silicon, to understand where within the disk in terms of how far from the sun they formed. And finally, each type of meteorite that we went through a moment ago tells us something different. So if we put all of this together and look first at the carbonaceous chondrites, so these are, again, the meteorites that come from the unprocessed planetesimals. They haven't been heated yet. They have bits in them, like this calcium aluminum rich inclusion here, that trace different ages within the solar system. So these different components, this particular component, the calcium aluminum rich inclusion, traces the earliest stages of planet formation. This marks the t=0 moment for planet formation in our solar system. It says that at that point in time, the disk was very hot, and this means that you basically were condensing minerals directly out of a hot gas in the inner disk to form the pebbles that went on to become the planetesimals that formed later on. We can also see from these, another component here, you see this very spherical shaped thing up there that's iron rich. So these represent the centimeter-sized pebbles that existed throughout the lifetime of the disk from which the planets accreted. And then finally, there's an additional component, which is essentially the dark material in between all of those other little dots. And this is called a carbon-rich matrix. And it samples tiny dust grains that were age-dated to be around 5 million years old in the solar system. And this basically tells you they were the last part of that planetesimal to come together and stick together. And that means that there was a generation of planetesimals that formed late. Then there's an additional, the next meteorite that we look at are the iron meteorites. These are the ones that were from the cores of the planetesimals that got big enough and hot enough to restructure themselves into something that looks like Earth. So these cores that turned into iron meteorites, they actually formed very, very early, almost immediately after this T=0 moment that was measured from the hot material very close to the central star. And they differentiated, or they were restructured into something that looks like Earth within about 1 million years. Then we can look at the next. Well, this means that effectively, rather than forming planets just at this stage, which is around 1 million years old, they actually formed already very early at the stage where the disk is still embedded and the system is still connected to its molecular cloud, so much earlier than we expected. If we look at the next meteorite, the achondrites, this was the one that came from the mantle or the crust of the planetesimal after it had been restructured. We see that this, this example in particular came from Mars, when Mars was being assembled. So this meant that Mars reached its 50% of its current day mass by about 2 million years after this T=0 moment. So this means that essentially, by the time you get to the stage where you see these pretty pictures of like the giant planets in the gaps in the disk, the rocky planets have already formed, and all of the action essentially happens very early. And then finally, the last type of meteorite was another one of these ones that's the unprocessed rubble piles. And they have components in them that indicate that were age dated to around 2 million years old. And these particular ones are carbon poor, whereas the ones over here were carbon rich. And what this implies is that somewhere around 1 million years after the T=0 moment, there was a gap that opened up in the disk and cut off the pebble supply between these two types of planetesimals, separating them. So there was no communication between them, and that's why they have very different compositions. And the easiest way to do that is by having Jupiter open up a gap, sort of like you saw in this cartoon for planet formation. Jupiter opens up this gap, and that blocks material from moving in toward the inner disk, and that means that the areas where these particular meteorites and planetesimals came from, they end up being carbon poor. So this is perhaps a better cartoon to illustrate this. At early times, you had mixing between the inner disk and the outer disk, and everything was mixing together. So you had a similar composition in and out. But at some point, Jupiter forms, opens this gap, and then you start to evolve different compositions in the inner disk from the outer disk. And the outer disk remains carbon rich because it's colder, you have more ices, and the inner disk becomes carbon poor because it's warmer, and you don't have ices that can survive there. So, yes, so we're mixing. These will end up being carbon rich, these will be carbon poor. So, essentially, Jupiter is really thought to have caused this by opening up a gap, like you saw with the planet formation here. Now, another cartoon just to represent this, this is a plot where you have time on the x-axis, and the size going from dust up to planetesimals to Mars-sized planets to something like one Earth to then Jupiter size on the y-axis, the size of the planet. And this is the path that we think Jupiter took. That essentially, right here you have your T=1 moment where you have these calcium aluminum rich inclusions. Then you have something like a streaming instability that happens where you again collapse a small cloud of dust and gas down to form a planetesimal. That planetesimal formed beyond the water snow line, so it contained both dust but also ice. And then through that first generation planetesimal, then through pebble accretion, grew up until it was large enough to open a gap. And that was at something like 20 Earth masses in size. And then from then on, you had runaway gas accretion from the disk that caused Jupiter's atmosphere to form around it. And then you end up with something like Jupiter. And in contrast, what we think happened with the Earth, it started off at the same point after you had CAIs and you had your first generation of planetesimals, but we think that Earth formed inside of the snow line. And because of this, it didn't have nearly as much mass, it couldn't grow quite as rapidly. So because of that, it grew very slowly over time and never got large enough to open up its own gap. And then at some point, you can see that Jupiter's already formed around here, but Earth continues to grow through the collision of other planetesimals with it. And then you end up having a final impact that delivers the carbon to Earth. So 50% of Earth formed here, consistent with Mars, and then eventually Earth is 100% formed. But the real question is, these are the paths that happen in the solar system, but what does this mean for other rocky planets like Earth? How would they move potentially in this diagram? Well, if you don't, like let's say we come back over here, we see most of these planets are in this size, they're larger than Earth but smaller than Neptune. We don't see very many gas giants. So what if we take the gas giant out of the equation, we remove Jupiter, and see what happens to the rocky planets? In this case, you don't have a Jupiter, which means you never open a gap. And in that case, we think that once you have your stringing instability, your first planetesimal could essentially keep growing and end up forming something like a small Neptune. Probably still needs to form outside of the snow line, but maybe at a distance where you don't have quite as much ices as we had for Jupiter. And then in contrast, if you don't have that larger planet blocking the material flowing in, you essentially end up forming something that's larger than Earth because you have more food for it coming in from the outer part of this, so it can eat more. And the material that it does eat contains more carbon. So you should have something that's larger than Earth and more carbon rich. So in the absence of Jupiter, rocky planets should be larger and they should contain more carbon. So this is what we would expect based on planet formation theory and what we see in the solar system. So how does this compare with what we see when we look at observed protoplanetary disks? Now, there are going to be 3 points that I'll address about this. The first is, do we see this T=0 moment in any other systems besides our solar system? The second one is, do we see evidence for the formation of gas giant planets early on by, say, looking for their gaps? The third one is, what is the carbon content of the rocky planet-forming region in different disks? Do we have evidence for this now? All right, so if we look at the T=0 moment, we go back to this diagram. That's right here where we have these calcium and aluminum-rich materials that condense very early. However, this stage in planet formation is largely a black box to us. And this is because we have at this stage, you have the star surrounded by a disk, surrounded by this envelope of material that moves gas and dust from the cloud onto the disk. And this envelope is very, very thick, and it's like a dusty cloud that hides that inner part of the disk. So we can't observe the inner part of this disk directly in very many systems. Now, on the other hand, we were recently able to find a system where it looks very similar to what we think the sun should have looked like at this age. So this is a protostar called HOPS 315. This is an artist's impression of it. The central protostar is there. It drives a jet. It has this envelope around it, but it's tipped toward you at just the right angle so that you can actually see down through the envelope to the central region of that star. And we think that this system, HOPS 315, is a very good match to what the solar system looked like at this age. It's in a clustered environment called the Orion molecular cloud. We think that the sun formed in such an environment where there were other stars very close to the sun and giving off a large amount of radiation. We think that based on the measurements of the star mass itself, it looks like right now it's about half the mass of the sun, but it will accrete enough material that it should grow to be the sun's mass after 1 million years. So it's on the same trajectory to become the same size as the sun eventually. And if we look at the mass of its disk is really, really big and really dense and very massive, similar to what we think the sun's disk looked like at this stage. So we looked at this system with the James Webb Space Telescope. And just to give you a little bit of information about JWST, the James Webb Space Telescope, which I'll call JWST, it was a joint NASA, ESA, and Canadian Space Agency mission that launched on October, well, okay, this was actually launched in December 2021, sorry, that's the wrong date, it was Christmas Day. Initially, it was going to have a 5-year lifetime, but it was actually, they saved enough fuel on launch, so now it's going to have a 20-year lifetime, so we should get a lot of really interesting data from this over the next few years. It is a mission that a lot of people at Leiden Observatory have worked on, so I'll try to highlight a few people's work as we go through the rest of the talk. Okay, sorry, that was not all right. Basically, the reason why we look at things with GWST is that in the infrared, we're actually able to observe the dust and gas content of these disks directly through spectral signatures. So when we look at this system, and we aim GWST straight at the center right here, and we blow up what we see from it, you get this series of lines and wiggles. Now this part right here, where you see what looks like white hair, those are actually absorption lines for silicon monoxide gas. And this is a type of gas that you only see if you were to take a rock and burn it up at really high temperatures. And this is because rock is made out of silicon monoxide plus some magnesium plus some iron. So we see rock that is burning up, but at the same time, what you see here in these, the bottom of this spectrum here in white, you see all of these little up and down wiggles like that. And if you look up at the top, you can actually see in 3 different colors a series of laboratory data that was taken of different types of rock when it was heated to high temperatures. And you can see that a number of these wiggles match up very nicely with what we see in the spectra. So this suggests that we are seeing these high temperature rocks, and that these rocks actually condensed out of this gas vapor. So basically, we burned up interstellar rocks as they were falling in close to the star, and then the disk cooled enough that this vapor condensed back into new rocks that had this specific form that you can use these laboratory data sort of to fingerprint which type of rocks we were seeing. And the type of rocks that we were seeing turned out to be very similar to the kinds of rocks that we see in meteorites at this t=0 moment. So there's some calcium rich material. There's also these crystalline materials over here that all have the SiO gas in them. So we think that this is the first example where we're seeing this t=0 moment in the solar system's planet formation timeline. And you might say, well, this is just one object. How significant can it be? But it turns out that we see another system like this. So this one is not unique. There's another one where we see this SiO gas, silicon monoxide gas. So this means another system where rocks are being burnt up. And in this system, we also see strong crystalline mineral signatures as well. Now, my PhD student, F.Kaiser, who is hiding over there in the corner, is working on this right now. It's her first paper, but we're really excited that this is another example where we think we see this t=0 moment. And an interesting aspect of this is that this protostar also has a very massive disk and a star that should be similar to the sun when it's done forming. And this maybe raises the question, is the reason why we haven't seen this stage before because it only works in stars that have a sun-like mass? And maybe the reason we haven't seen it before in the other systems is because they're too low mass, so they didn't have a disk that was massive enough to produce this stage. This is something that we're exploring in future work. Now, we move on to the second part, second point of comparison with observations, and that is looking for signs of gas giants that form in protoplanetary disks, and whether those form early or not. So this is a picture that was taken with the ALMA telescope, the Atacama Large Millimeter Array, which is a collection of 60 telescopes in Chile, more than 60 telescopes in Chile. And it essentially is very good, while JWST is good at measuring dust and gas composition through these spectral signatures, ALMA is instead good at looking at spatial structure for dust as well as gas compositions. So ALMA can basically make these really great images where you can start to see different ring systems in these disks. So when we look at young disks with ALMA, say ones that are around 100,000 years old up to maybe 1 million years old, we start to see that about a third of these young disks show evidence for having centimeter-sized pebbles already in their disks. And these were the pebbles that are necessary to have as some kind of feedstock to then collapse to form these first planetesimals. So they're a critical first step in the formation of rocky planets, or really any kind of planet at all. The fact that a third of these disks have pebbles already could mean that the conditions are ripe to actually form something like Jupiter. Now, it's very tempting to look at this, this picture and actually say maybe you have some of these rings are deep enough that you could actually have a Jupiter-sized planet forming within it and going around. And this is what we think in some cases probably is happening. So a handful of these disks have gaps or holes that are relatively deep, and these suggest that you actually could have gas giant planets like Jupiter that have already formed and are cutting off motion of material in the disk from the outer disk flowing in. However, you can tell that 1/3 is not 1, right? Which means that actually 2/3 of these disks don't have enough pebbles to form Jupiter-like planets. And many, while many of the disks that we'll see on the next slide that are mature disks have gaps, a lot of them actually turn out to be relatively small and don't have gaps. So this means that gas giant planets can't be a natural outcome for all disks. It's probably just this 1/3 that really have gas giants. So if we follow up on this point and look at mature disks, this is a gallery from one of the other groups doing planet formation at Leiden, Nika Vargamar's group with one of her PhD students, Osmar Alvarado. So you can see in this diagram, all of the purple's just the background, but the orange and yellow colors are the locations where you have disks. And if you get a feeling for the size, you can see that some of the disks are quite big and show ring structures like that. So actually about 2/3, let me rephrase this, 1/3 of these disks are large and have this kind of structure. The other 2/3 of the disks do not have structure. They have sizes that are smaller than the orbit of Neptune, which is given all the way down here at the bottom right. So there 2/3 of the disks are very small. Now, if you zoom in on the smallest disks and blow them up so they're a lot bigger, now we're comparing it with the orbit of Jupiter, which is down here. You can actually see that even these smallest disks a lot of them have no gaps. So for example, this one has a gap, the one in the upper corner has a gap, but a lot of the others are actually centrally peaked with a relatively small disk. And some of these really just have the central peak, there's no other structure in them. They're smooth, completely smooth. So no gaps. And this means that in these disks, because they don't have gaps, carbon-rich icy pebbles should be able to flow from the outer part of the disk into the inner part of the disk without getting stopped. So the inner disk should be more carbon-rich. And the consequence of this is that we would expect carbon-rich super-Earths, or things that are rocky planets that are larger than Earth, in these disks instead of carbon-rich planets that are Earth-size. So this is evidence for that alternative case that we talked about, where you don't form planets like Earth, in 2/3 of the cases. So can we actually see compositional evidence for having carbon-poor or carbon-rich regions in these disks? And for this, we turn from ALMA back to JWST because we need to look at compositional information. So this is some other work by Leiden PhD students, Larissa Glassbaum and Navina von Bishop's group. So these are cartoons that represent what would happen to the composition of these disks if you cut off the pebble supply by opening a gap. In the first case, where you have no gap, you have the water snow line here, which is the line where we said that outside of it you can freeze out water, inside of it everything is water poor. But water is not the only type of ice in these disks. You also have carbon monoxide ice, carbon dioxide ice, which we had mentioned on an earlier slide. So if you have, each of these ice species also has their own snow line that corresponds to it. And in this case, you would end up with an inner disk that was rich in both water and also carbon dioxide if you have no gap. If you do have a gap in the disk, say the gap is between the water snow line and the CO2 snow line, then you would expect that you end up not allowing the water-rich material to move into the hotter region where it can sublimate into the gas phase. So you wouldn't detect water in the gas phase of your inner disk. And instead, you would expect to see mostly CO2-dominated disks with no water. Now, we can essentially say this again, the rocky planet region should be water-rich. If you have the gap, then you end up having water vapor-poor regions, and then they should either be rich in carbon if the gap is inside of the CO2 snow line, or potentially poor in carbon if the gap is further out. Now, what we actually see when we look at the James Webb Space Telescope is exactly what this cartoon has been setting up. Some disks here have a very rich spectrum of all of these colored lines. Most of those are actually water lines. So this particular disk is water rich. This is from another set of papers by, of course, Observatory and Melissa McClure of the Venus group. And if you look at other disks, instead, you can see that they don't really have very tall lines like this. The lines are very weak, and instead you see a very prominent CO2 feature right there relative to the water lines. So this is fitting exactly this scenario where some of the disks are cut off from resupply by the material, the icy pebbles moving in from the outer disk. Now, we can go a step further in this and say, all of these JWST observations, we're looking sort of over here in the part of the disk where we think that the planet should actually be forming. But we can look interior to where the planet is formed, right where that material is going to be eaten up by the central star. And if we do that, say this is a very old disk, F.Kaiser, which is 8 million years old. It's one of the closest disks to Earth. If we look at this at all the wavelengths, we see that it has a series of gaps here. Now, each of these gaps could potentially host a giant planet. So we would expect that these gaps should cut off the supply of icy material from the outer disk. And what we can do is, if they cut off that material, then essentially at the edge of each gap, you would form a trap that holds that material back. And you can think of these traps sort of like the kind of sieve when you make pasta. You pour the pasta and the water into the sieve, and that holds back the pasta, but the water that comes out the other end has a lot of starch in it, right? So you could theoretically measure the amount of water that you get, the amount of starch in the water, and work out how much pasta got left behind in your sieve. So we can do the same thing by measuring the gas phase composition at this point, very close to the star, and see how much material got left in the trap, in the dust trap where the planetesimals form. So we did this in a paper a few years ago, and in this case, this is a plot of the gas phase abundance for different elements. And the elements are organized by the ones that are in ices on the left-hand side, and the ones that are in rocks on the right-hand side. So the first thing to look at is that the material in ices is about, there's 100 times less of this material than there is in the sun. And the sun's line is here, like straight down the middle, as a reference. We can also look at the amount of rocky material. The fact that there's 100 times less icy material means that there's probably a trap here, trapping the ice further out in the disk and preventing it from coming through. Now we can also look at the rocky material over here. The rocky material is 10,000 times less than what we see in the sun. And this suggests that not only is the rocky material also held back along the icy material in that trap, but that there's a second trap further in, right around where Earth would be forming. And this may hold back rocky material inside that ring. And this ring should be relatively carbon poor, whereas the ring outside should be carbon rich. And finally, if we look at the pattern that you see in the abundances, if we compare it up here with what we see in meteorites, you see that same hooked pattern, where there's less carbon and oxygen and nitrogen, and there's a lot of rocky materials. And we see the inverse or mirror pattern of that in the disk gas, which suggests that the material that's being held back in the disk is actually the same sort of material that goes on to form meteorites. So with this, we think that in that inner dust trap, we are forming potentially planetesimals that could go on to have a similar composition to Earth. And we also think that in that outer disk trap, we are forming planetesimals that could have a similar composition to comets. So we can put the two together and say we essentially have the ingredients to form a rocky planet that is similar to Earth and deliver a tiny amount of volatile materials to its surface after it forms. Now, There are missions that will, including JWST, that you'll hear about in the later Kaiser lecture talks in this series, particularly with David Snellen, where they will actually measure the composition for rocky planet atmospheres. And these should tell us something about whether indeed they are carbon-rich for the ones that are larger than Earth or carbon-poor. So I will not belabor this point, but you can see that there is water and CO2 that are in this exoplanet spectrum model. And I think you'll see in the later talks in the series how much of these are actually in the atmospheres of the planets in which we're interested. And that will basically confirm whether these two types of planets have more carbon than Earth, which is what we think they should. So to conclude, we know that Earth is carbon poor, and it's probably because Jupiter cut off the supply of material that was feeding it from the outer disk while it was still growing. We also know that planet formation theory suggests that otherwise, if Earth hadn't had Jupiter outside of its orbit, that we would expect Earth to have grown larger and be more carbon-rich. Finally, most rocky planets are between Earth and Neptune in size. And we know that 2/3 of the disks that we see appear to be primed to form these larger carbon-rich rocky worlds, whereas only 1/3 of them appear to be ready to form systems that have something like a Jupiter mass planet and something that would be potentially carbon-poor Earths. So in essence, we should expect to find some carbon copies of Earth in the coming years, but we shouldn't expect all planets, all rocky planets, to be like that. And thank you.